because I was not able to see very well what was written on the blackboard. Even though it was like long time ago, I perfectly remember my very first day I went to class to my brand new glasses, and it's like all these blurry shapes became like super sharp lines. And I get this is somewhat similar to what happens to the study of the internal kinematics of the Magellanic Clouds, thanks to the launch of the Gaia data of Gaia. So in this talk, the Magellanic Clouds with high resolution glasses, I'm going to be talking about what we have learned in the last years thanks to the Gaia mission. So first of all, I'm going to start by showing this picture that I guess that if you have been like in any other Gaia talk, you have seen like plenty of times. In here, we can see very clearly, like the inner region and the disk of the Milky Way, where we can have like some dust lines in the galactic center. However, today I'm not going to focus on the Milky Way disk, but I'm going to focus on these two overdensities here, which are the LMC and the SMC, which is the acronym of the large and the small Magellanic Cloud, respectively. Just to give you like a bit of context of how those galaxies look on the sky, this is how Gaia would see the Andromeda galaxy. So the LMC and the SMC are less massive than the Milky Way and Andromeda. However, they are like so close that we can still see them like very big and bright on the sky. So now if we make a zoom in and we focus on these two galaxies, I would say a few words about them. First of all, if I talk about the large sibling of the couple, the LMC, I would like to emphasize, first of all, its mass, which is, as I was saying before, 10% of the total mass of the Milky Way. So it would be like 10 to 11 solar masses. And it is classified as a dwarf spiral galaxy. So as an spiral galaxy, this means that all stars lie in a plane. However, this plane, even though it may look that it's completely face on with respect of our field of line of sight, it is not. There are some estimations that it says that this inclination is of the order of 20-30 degrees approximately. Also, there are some other clear signs of disequilibrium or stuff that is going on with the LMC. First of all, is that we can see here one single unbroken spiral arm. And also we can see that it has a bar whose center doesn't correspond with the kinematic center. So it's an off-center and out-of-plane bar. On the contrary, if I focus now on the small sibling of the couple, the SMC, what I would like to emphasize is, first of all, its mass. Here there is a 1 to 10 mass ratio with respect to the LMC. So this means that it's a 1% of the total mass with respect of the Milky Way. And it is, however, classified as a dwarf irregular galaxy. So this one is not a disk, but it has like a more distorted shape, mostly in the line of sight. So yeah, here we see that we have a distorted shape, and also that there are like some clear signs of disequilibrium, such as the Magellanic Bridge. So now, if we take this system as a whole about the LMC and the SMC, you may be asking, no, okay, what makes that system interesting? Why should we care about those galaxies? First of all, I would like to emphasize that those are the closest galaxies to the Milky Way. So this means that we have astrometric information for millions of stars, thanks to Gaia data. And secondly is that we don't live inside these galaxies, no, as it happens to the Milky Way. So here we have like a complete view of the galaxy. Since we don't live inside it, we are not only able to see one part of the galaxy, but the galaxy as a whole. Secondly, what I would like to emphasize is that they are in a strong interaction between them. No? For example, this Magellanic Bridge is one of these clear signs of stars from the SMC being stripped towards the LMC. So taking all these two things as a whole, what I would like to emphasize for you and to take as a take-home message is that the LMC and the SMC are the perfect laboratory for testing methodologies and models designed for the study of external and interacting galaxies. So now that I have introduced the system as such, I will give you the outline of this talk here today. First of all, the motivation, which I already did, and now hopefully you will care about the LMC and the SMC. Secondly, I will give you a bit of context of what we know and what is Gaia for those that you don't know. Thirdly, I will talk about how we can make clean samples of both the LMC and the SMC and the corresponding kinematic analysis we can use with Gaia proper motions. Fourthly, I will talk about the LMC bar pattern speed, what can we say about that. Then we will talk about the LMC 3D structure. Then I will talk going a bit farther away, we'll talk about the outskirts of the LMC and talk about the S3 stream. And finally, I will conclude with the main conclusion of this work. So yeah, let's go now for context. So yeah, the most of the data I will be using during this presentation is Gaia. So for those that you don't know Gaia, if I had to summarize it in one single sentence, I would say that Gaia has been providing like astrometric, photometric, and spectroscopic data for almost 2,000 million stars. In order to put in context this number, no, you may wonder if it is like a large or a small number. I will start with the pessimistic point of view. I would say that this number is small because it only represents 1% of the total number of stars expected from the Milky Way. However, if we want to be optimistic, I would say that Gaia has been improving a lot by his astrometric predecessor, who is Hipparchus, who observe much less stars. No, so for each star that is on the Hipparcos catalog, there are 20,000 stars in Gaia catalog. So yeah, it's a factor 1 to 20,000. So in order to visualize this, it's like also it's not only about the numbers of stars, but how far we can reach. Imagine that this is what Hipparcos was able to see, which is mostly solar neighborhood. Gaia is able to reach much, much farther away. No, so reaching the galactic center, we can see spiral arms in the Milky Way, and so on. And now we take like this artistic impression and see the Milky Way from top. Here we can see like how Gaia is scanning the Milky Way. And again, the sad part is that since we live inside the Milky Way, we have very good data, but we are not able to see the galaxy as a whole. Something that doesn't happen for the LMC and the SMC. So yeah, now we come back into the Gaia data, and here the nice part about this picture is that this is not a artistic impression. This is real Gaia data where each pixel represents the convolution of thousands of even millions of stars scanned by Gaia. No, so you know which is the photometry. So the idea you can make these kind of colorful maps due to that you know the colors of these stars. So yeah, now that I have been giving the context, the first scientific case I would like to address is the LMC clean samples and the corresponding kinematic analysis. So this was presented in my very first paper during my PhD, named Kinematic Analysis of the LMC using Gaia DR3 data. And the objective of this paper was twofold. The first one is to make a neural network classifier for the selection of clean LMC samples. Yeah. So in order to motivate the problem, no, imagine this is an artistic impression of the galaxy we live in. No, we have the Milky Way, which has a disk. It also has like an stellar halo, and a dark matter halo. And the LMC, imagine that this galaxy here. No. So when we observe towards the LMC, we have to go through the Milky Way stellar halo. And in the end, what we have here, no, is like we have a combination of these red and yellow stars representing this, no? Some stars that are from the LMC and some stars that are from the Milky Way. So the first problem to know is like, okay, how can we know which star corresponds to which galaxy, no? The first idea is not, okay, this shouldn't be trivial if we know if the star belongs to the LMC through the distance. The answer is yes and no, because Gaia sadly is not producing distances, but is measuring parallaxes, and these parallaxes can be used as a proxy to estimate distances. However, since we are talking about galaxies that are like around 50, 60 kiloparsecs away, the parallax is not a good proxy because the error is of the order of the signal, so we cannot use them to measure individual distances. So we need to go something more sophisticated and trying to do in another kind of strategy, no? So in here, where it comes, this LMC Milky Way classifier, which is based on a neural network classifier, so AI and machine learning. Here, what we take as an input is Gaia astrometry and photometry, so it's like proper motions, positions, and the colors of the stars. And we provide as an output a probability P of being an LMC star. So this probability, its domain will go from 0 to 1. So something like this. If your star after the classifier goes and scores close to 0, this means that the star is highly likely to be of the Milky Way. On the contrary, if this star gets a value close to 1, this means that the star is highly likely to belong to the LMC. However, we want this classifier to be binary, so in order to get this, we need to impose some probability cut. If the probability is above this central number, will be LMC sample. If it's below, it's going to be Milky Way sample. So something like this, for example. So now the thing is that if we select a probability cut such as this one and a small one, this means that we are going to be prioritizing completeness in our LMC sample, no? So in this middle range probability, we are going to consider them to be of the LMC. However, if we want to get more strict and we move this to higher probability cut, what we are going to do is to prioritize purity in our LMC sample. So this means that the stars that are going to enter in our LMC are going to be highly likely to really be from the LMC. However, we are going to lose many of them probably and go into the Milky Way sample. So here is like this trade-off in order if you want to go more pure or complete. So what we did in this paper is exactly is to provide the community this probability P for each of the different stars. And then we propose three different samples. Depending on the scientific case, you will want to prioritize completeness or purity. So for this complete sample, what the probability cut that we suggested is 0.01. The second one is the optimal sample, which is kind of the trade-off between completeness and purity, which is a probability cut of 0.52. And the third one is the truncated optimal, which is the same cut, probability cut as the optimal one, but we only select the brightest star, since probably are those the ones that the classifier is going to be performing better. So again, this catalog is public and available online. So if you want to play, you just need to go to the CDS. So now what I'm going to show now is like how these different samples look like in density, no? So here on the left column, what we have is the LMC sample, and on the right we have the Milky Way sample shown on the sky, no? So alpha and delta. And in here we're going from more complete on top and from more pure on the bottom. Here we can see, for example, no, that in the more complete sample, I think you cannot see my cursor, whatever. You can see here that on the left sample you have like some, the outskirts are more yellowy, so this means that we have some stars there. However, for the optimal, we start like losing this information. In the outskirts, probably a sign of Milky Way contamination. So the nice thing is that, as I was saying before, okay, let me go here. As I was explaining before, Gaia is not only providing astrometric information, but it's also providing photometry, no? So this means that for each of these individual stars, we can determine which is its color, no? So we can take these Gaia G magnitudes, convert it into fluxes, and to see which is the total flux per pixel, no? And try to make images from these datasets, no? So here what I am showing is like these very same datasets converted into these CCT-like images by taking into account the Gaia photometry. So here on the left, what I'm showing is the LMC base sample. So this is where we still have LMC and Milky Way stars. And here what we are going to see is like how the number of stars decreasing if we go from more complete into more pure sample, no? From these 12 million stars to 6 million stars. Now, in order to like convince you how good this Gaia dataset is in order to study the LMC, I will focus on this sample, the complete sample, and make a zoom in image. And in here we can see how, again, no, for each of these different pixels is the convolution of thousands stars in the Gaia catalog. And we are even able, no, to even make a zoom in region and to focus more inside, for example, and show how good the quality of the data is for the LMC bar, for example. So this was part one of the paper, so providing to the community these samples of clean LMC stars. And the second one is to make the kinematic analysis of the in-plane velocities. No? As I was saying before, the LMC is at this galaxy. However, it is not face-on with respect to us. So what we are going to do is to correct this and to go into the in-plane coordinates. So in order to motivate this problem, imagine this is us living like in the center of this celestial sphere, no? And imagine that we have here the LMC center. So I was saying before, what we are going to do now is like, okay, what we are observing is like this LMC in this tangential sky plane, no? Which are all the images I have been showing. However, the LMC lies in this plane here, which again, no, is like around 30 degrees with respect of the tangential sky plane. So what we are going to do is to move from these Gaia observables, we live in this celestial sphere, into the LMC plane. So when we do so, we can get this kind of different maps. Here on the left, what I am showing is like the LMC on these in-plane coordinates, which represent this x prime and y prime, and these black lines represent which are the density contours of the LMC. No, so we can see the bar in the center, and then we can see the spiral arm, which breaks and goes into the other part of the galaxy. And then here on the left, what I am seeing is the radial velocity maps. So this means if the star is moving towards the center or farther away from the galaxy. And the other one is the residual tangential velocity, which means how fast the star is rotating with respect to the rotation curve. So here we are removing the axisymmetric part, and we see if the star is rotating faster or slower. So let's focus on one of these, for example, in the optimal sample, and let's say some stuff about that, no? First of all, if we focus on the inner region, so this is the LMC bar, we confirm that there is a quadruple trend, and that is asymmetric, no? This quadrupolar pattern is kind of expected from this kind of X1 orbits that populate the bar. However, what we can see here is that it is not evenly distributed, no? Like the blue part is not as big on both parts of the bar, no? So it is like maybe this part is like more representative than the other counterpart, no? This can be produced, for example, by the inclination of the bar and stuff like this. So yeah, this is something that we can use in order to say more about the LMC bar. Now, if we move towards the spiral arms, we can see that the part attached to the bar has an inward motion, so it's like colored blue in VR, so this means that it's negative radial velocity moving towards the center, and the rotation is faster, no? Red color, this means that the stars are rotating faster the rotation curve. And then here we can see that this inflow of stars from these outskirts of the LMC, that they are moving fastly towards the center. And this is something that we studied in another paper by another PhD student in Barcelona named Marie Scholk, in order to see if this is a product of the Magellanic Bridge or not, or is a sample bias. So if you want to know the answer, you can check this paper. We see it on the archive. So yeah, this was what from the part of the LMC clean samples and the kinematic analysis. I hope it was kind of clear. So now the idea is that we want to use this kinematic analysis to do some science with them and to learn something, no, about the LMC. So first of all, now what we're going to do is to focus like from the inner regions more towards the outskirts. So now we'll start with the LMC bar. So the results of here were obtained in this, were published in this paper, the LMC, the bar pattern speed of the LMC. And the idea and take home message that you should take in this paper, which is a bit lengthy and it's a bit tough to understand in some parts. What I would like you to take home now is like we use 3 different methods in order to infer the LMC bar pattern speed, using both Gaia proper motions and line and velocities. So first of all, one of the methods that we use is the Tremaine and Weber method, the TW. The other one is the bisymmetric model of the tangential velocity, where you can infer which is the corrotation radii, and then as a consequence, which is the bar pattern speed. And then the third one is this Dennett method, which was published a couple of years ago, intended to be used on single snapshot simulations in order to know which is the bar pattern speed. And it's a modification of the TW method in the end. So if I had to summarize, again, no, like this paper is kind of dense, but if I had to summarize like the main results, I would say that all 3 different methods provided 3 different values. And what I'm going to do in this talk today now is to focus on the values obtained by the Dennett method, which I think is like the most trustworthy ones. When applying this Dennett method to the LMC data, no, what the method does, again, no, here we have like the density and we have like the different velocity maps. What we do is to mask the bar region and determine the pattern speed. When we do that, we obtain a pattern speed of -1 kilometers per second per kiloparsec. So this means that the LMC may be hosting a non-rotating bar. So this is something that was quite surprising for us when we did the paper. And we tried to hypothesize what could be the cause of this result. Yeah, first of all, what we wanted to say is that this has been already found in some numerical simulations, like to find bars that are not rotating, but for very specific configurations. For example, there is one paper, no, that they claim that you can flip the rotation of a bar if you have like a dark matter halo, which is counter-rotating with respect of the disk in a very fast way, no. However, this is, how realistic this scenario is or not is kind of complicated. So yeah, we wanted to go slightly deeper and to know which could be exactly the cause, no. Something that we wanted to know is like maybe it has an external origin, so the interaction with the SMC and or the Milky Way maybe can boost the stopping of the LMC bar. However, there are like some problems or issues that comes, that a bar non-rotating means that there is no corrotation. So yeah, maybe this is a transient effect that cannot stay for long. However, we must know that these results can be sensible to dust extinction and completeness of the Gaia catalog in the very most inner region of the bar. Or maybe there is a counter-rotating M equal 1 mode that is compensating this pattern speed estimation. So what I would like to focus now and what we did later in a follow-up work is to know if this possible external origin, which is the interaction with the SMC and or the Milky Way, can explain the bar to be non-rotating. So this comes in a letter we published at the beginning of last year with Santi Roca Fábrega, a researcher also here in Lund, in this paper. No, tidal interaction can stop galactic bar on the LMC non-rotating bar. No, so there is a bit of a spoiler on the results, but yeah, basically what we did in this paper is to show that indeed the SMC LMC interaction can stop the LMC bar. So here what we use is this Kratos suite, which I will not go into a lot of detail, but basically it's a suite that I ran during my PhD thesis on LMC, SMC-like interactive models, also with the Milky Way present there. And in out of these 28 simulations in the suite, we found indeed how the LMC bar can stop due by the interaction to the SMC. So here we derive the bar pattern speed in two different ways. The first one is by finite differences. So in the end, those are simulations. So we have time evolution. So it's kind of straightforward to know how the bar is rotating. And the other one that we use is to apply this Denon method, no? So we wanted to see if indeed, if we find some moments where the bar stops, the Denon method is able to recover the result in order to give some trust into the result we obtain with the data. So here there is a video that I think is not going to work. Yeah, exactly. So I think I will have to let me unshare and go here. I have the video. Yeah, so here the video we want to show, here we have the density. So here we will see at some moment how the bar stops rotating. And here we have the evolution of the bar pattern speed, no? So here we have the LMC rotating. The SMC will come anytime soon. Exactly, the SMC comes. And here we can see how the bar stops rotating for a while until it continues the rotation again. So I can show you the video once again. So here we have the bar of the LMC rotating. The SMC interaction comes and the bar stops. And then after some time continues rotating. So I will Something that we found interesting is that this rotation is stopped for almost like from 1 to 200 million years, which is kind of what the expected time of the last interaction between the LMC and the SMC. So in this sense, like this is kind of in agreement in terms of the timing of the interaction. Yeah, there was a follow-up paper on that, which I was also related and done by Valentina Araya. And here what we saw is like how we analyze using this very same method, the Denon method, how the pattern speed changes across different stellar populations. And here we found how indeed also the pattern speed is consistent to zero for some of the stellar populations, but not all of them. Okay, so this is like what is for the LMC bar pattern speed, and now for the last 15 minutes, I will go for the LMC 3D structure and the stellar stream. So yeah, remember like these velocity maps I showed before, no? Those maps were obtained only using astrometry by Gaia, so just using proper motions. So here the samples as of the order, as I was saying before, no, from 12 to 6 million stars, depending how complete or pure you are. However, what you can do is also combine it with Gaia line of sight velocities, who also provides for a smaller subset of bright stars, but there are some stars with line of sight velocities. And you can also determine these very same maps having the third component of the velocity that was missing. So the idea we can see that overall the trend is kind of similar. However, again, what we are doing is like to lose part of the information in the outskirts because we don't have line of sight velocities here. However, there is something that we win by including line of sight velocities is that we have access to the third dimension also of the velocity. In this case, is the vertical velocity. So this means how stars move perpendicular to the plane of the LMC. So in here, this is on the very same paper from I showed you on 2023. We saw like this bimodal trend with half of the galaxy moving upwards and the other half moving downwards. So in this context, no, what we wanted to do, like 1.5 years, 2 years ago, I joined the SDSS-5 collaboration, and what we wanted to do is to use the line of sight velocities from SDSS to continue studying the LMC 3D structure. So yeah, this is inside the context of the Milky Way Mapper survey of SDSS-5, and this combines line of sight velocities from both apogee and BOSS. Yes, so the scope of this work was, the idea was to use new line of sight velocities to improve the LMC vertical velocity maps. And yeah, this paper was published in early last year, named Vertical Structure and Kinematics of the LMCTs from SDSS and Gaia, where Danny Horta was second author, that I think that some of you know him very well. Exactly. So first of all, I'm going to start introducing the dataset used in this project. So again, here I will be working again on the same coordinates as before, no? So here are x prime and 1 prime and the LMC in plane coordinates, so where we already correct from this inclination. And here I'm going to show you some different panels, no? On the top column, we're going to talk about this complete sample, and on the bottom is this optimal sample. What we wanted to see is that those results, the results that we obtain, are consistent regardless the classifier that we select. And the different columns referring to different datasets that we're going to use, being the ones from SDSS, the one from the left, Gaia, and then the combination of all three, no? So this is what we had before, only with Gaia, what was published in this very first paper during my PhD. And this is what we gain with Apogee and BOSS. And we combine all this together. Here we can see that we have a much better coverage in the outskirts and in the inner regions. So here again, we have a factor or 3 times more stars. And again, not only more stars, but also like better coverage in the outskirts of the galaxy. And now what we can do is like, once we have the data, again, we can go and perform these velocity maps. And here is the combination of what we can see with Gaia and the combination, the combined. If I focus here on the combined sample, I would like to stress some stuff. Yeah, it's the confirmation of this bimodal trend. No? So this kind of wobbling that we see. And yeah, exactly. And what we wanted to see is like, okay, why do we see this, no? And there are like 3 different explanations that we had in mind that, and we wanted to test which was the most realistic one, no? First of all, is that maybe what we are seeing here is the time change of the viewing angle. So in other words, this maybe can be the effect of the precession of notation of the LMC disk. The other one is that maybe we are assuming a wrong plane, so the LMC plane is not well fitted. So maybe this makes this artificial dipole. And the third one is that maybe what we are seeing is the kinematic imprint of a warp disk in the LMC. Then here I'm not going to enter into many details because it can get like super dense, but what I want to tell you is like, yeah, first of all, the precession and notation, we're not able to explain this because still the residuals of the velocity was too high in order to explain this. And now we want to see is like, okay, the wrong assumed plane, yeah. It's not the case either. Again, we are not able to get rid of the whole kinematic signal by assuming this. And then the last one that we tried and we saw it is the warp disk. And here is where I'm going to get into the details. Yeah, first of all, what we wanted to do is to aim to find the new estimate of the LMC plane warp by minimizing B set prime for different radii. So imagine we have this velocity map. So now what I'm going to do is to split the LMC into these different rings and try to minimize and to find which plane is the one that minimizes the velocity for each of these. So in here, what I will show you now is as function of the LMC galactocentric radial distance, which is the x-axis. And in here we have the inclination on the top, and then we have the line of nodes position angle on the bottom. And here what we see is that indeed we don't have a constant value across the whole disk, but we are seeing here is like a variation of the inclination on the line of nodes as function of the radii. And this is consistent across the both sample, no? Both complete and optimal sample are shown here. There are like some small differences, but qualitatively it's kind of the same. So in here, what I would like to emphasize, no, is that we have an inclined bar, as I was saying before, no, on the inner region where we have like a different inclination with respect to the outer disk. And now we want to go is like, since we have like so much data, and this is something like super nice, we can go even like thinner in our splitting time, and we'll not only go to make like different radii cuts, but also on azimuth. So we'll have these different wedges. And now what I'm going to show is the results for this, no? So here is like how the inclination and line of nodes for the different samples changes basically. And here we can see some quadrupolar pattern, no? For example, if we focus on the leftmost panel, we can see how in the outer disk we have like orange, blue, no? So in here there's a kind of a signal of a warp. So once we have this data, which is the best plane that fits the different wedges, we are able to create, for the first time, the 3D maps of the LMC. Yeah, so this is here. Exactly. So here what I'm going to show, exactly, we use this data in order to make like the first 3D models. So here what I am showing. On two different colors, we can see the two different samples, the complete and the optimal, and the different columns represent different assumptions. No, the one on the left is the represent only taking into account radial variation and using this Tilted model used extensively during the last 30, 40 years. And in here we also made a different method that we named the inversion method, which what we will try to do is to make a continuous disk. So what I wanted to do is like kind of concatenating the different patches to have a 3D representation. No? And here what we can see now is like the results are consistent across different methods. In the end, it's like how you decide to represent them. And here we can see the evolution, and here we can see how if you go to the panels on the right, you can see now how the LMC clearly shows a warp and distorted disk. So yes, this is on the part of the LMC 3D structure, and now on the last 5 minutes, I will go on the LMC S3 stream. So if we talk about LMC streams to date, only 4 stream candidates are on the literature that have been selected using BHB and Blue stars. Those streams are named S1 to S4, depending on their own distance. This was initially done in the paper by Vasily Belogorov in 2016, when here you can see like the different streams that they were found using photometric filtering. Later, in 2019, Camila Navarrete, along with Vasily Belgorod, she did a spectroscopic follow-up of these streams and confirmed some of them and provided like new stellar candidates for all of them. No, here you can see the different BHB and blue struggles and removing some contamination from these samples. So here in this paper, what we are going to focus. Yeah, exactly. We are going to focus on this one, the S3 stream, whose results were published at the end of last year. So yeah, the objectives of this paper about the S3 stream are three. First one is to reassess the S3 existence, because again, not all this paper was done before Gaia DR2. I mean, Gaia DR2 was published in 2018, and Camila Navarrete's paper was 2019. However, that paper was only use line of sight velocities, no proper motions at all. So the idea is that we want to use proper motions from Gaia and to cross-match them with the already known sample to see if this is indeed a real stream or not. Positive results, spoiler, I can already tell you. Then, once we know that the S3 stream is indeed a stream, we want to expand the membership. So we want to create and to find new candidates using machine learning in a similar manner to what we did for the LMC Milky Way classifier. And then lastly is to model the stream and determine if S3 is associated to the Milky Way or it is really an LMC stream. So this is the field of view where we are going to be talking and working. This is again Gaia data plotted here, and this is like the training sample that we were starting using Camila Navarrete's sample. Here the arrows represent the proper motions. So here we can see how the stars are moving along the track. So yeah, this help us to confirm first the existence of this stream. Now what we want to do is to apply a neural network classifier, very similar technique to what we did before, and we obtain all these new candidate S3 stars. However, we can see on the proper motion that there is like some star that is not really matching. There are some arrows that they are pointing in very weird positions. And then what we have to check is to see how those stars lie in the proper motion space. No? And here, when we compare our new sample with the ones from the training sample, we can see that in our sample there is an overdensity around 0, so probably created by quasars that they have been misclassified as S3 star. So what we did is to apply another filtering by proper motions, and then we get this cleanest sample, where in here we can see how we obtain 1.5 thousand new stars of the S3 stream. So here we can see now that the nice thing is that initially we only have BHB, which are like these orange points here, and now we find stars that they can be also on the red on the red clamps. And now comes the part of the modeling. Here we're not going to enter into a lot of detail, but the idea that we try to do is to model this stream by taking into account also like all the information that we knew, both in proper motions and in distances for these BHBs. And what we found is that when performing orbit integration, is that most of our results that really matched well with the results is that this is indeed a Milky Way stream, and that just recently interacted with the LMC. So here on the top panel, we see the distance towards the Milky Way, so we can see like different orbits. However, the distance to the LMC is like very far away until very recently. So it's what we suspect and what we think is that it is a Milky Way stream that recently interacted with the LMC. So still the hunt continues for real XMC streams. Exactly. So yeah, this leads me to the end of my talk. So yeah, I will give you like some take-home messages about this talk here. First of all, I would like to tell you and to remind you that Gaia DR3 is providing more than 10 million LMC stars with proper motion information, and also some of them with line of sight velocities. And in 1 year, less than 1 year, we will have Gaia DR4 with even better results for the LMC. Secondly, regarding the innermost region of the LMC, I would like to emphasize that the LMC may host a non-rotating bar, and that the interaction with the SMC could be the natural explanation to this phenomena. Thirdly, that we are able to create the first 3D map of the LMC showing a tilted band region in the inner part and a warped outer disk. And that the S3 stream is shown as to be as the most distant extended Milky Way stream. However, it is not of LMC origin, so the hunt continues. So yeah, with this I finish, and I thank you for listening, and yeah, I'm happy to take any question.
Thanks so much, Oscar, for amazing talk.
Thank you.
Have you question? There's a comment. Thank you, Dr. Oscar. MCs have been significantly resolved with your work. From Alex, I guess.
I don't think so. Thank you.
I'm just wondering what will happen with the Gaia DR4. What will you see? What will your results And I'm just wondering, in your kinematic analysis, I think you treat the LMC as an isolated system, right? For especially for 6 million stars, we are choosing pure LMC. And when you are calculating kinematic values, which potential you are using? For Milky Way, we have many potentials like Milky Way potential, Macmillan, Coughton, etc. And how do you compute kinematics for LMC? I'm just wondering.
Yeah, in this case, what I am doing is just converting observables into another reference system. So in here, there is no need to assumption of any potential because in the end, I am not going into the action space or computing any kind of orbit. So in the end, it's like rotation matrices and yeah, correcting from systemic motion. So in here, there is no need to apply any potential, which is good because the LMC we know which is highly outside equilibrium. So yeah, it's like yeah, I wouldn't dare to assume any potential in the LMC. I don't know.
With your combined data with TSS, how many stars you have for LMC?
With SDSS 5?
Yeah, with
Yeah,
STS.
now there are more, but at the moment of the paper, I think it was like 80 or 90,000 stars. I think now we talk about 200,000, something like this. Like has increased even a factor of two or three with respect 1 year and a half ago.
I see. So I will wait for anyone have question for 1 minute. If you have, please unmute your microphone and ask to Oscar. Or he's so, thank you again. You can send email to him, may I say it, for your questions, and you can watch again this seminar from our YouTube channel.
Thank you very much for hosting me. Yeah, looking forward to meet you anytime soon in person.
Okay. So thanks so much, Oscar. I think
Thank you.
we should
Bye bye. See you. See you.
have a great day. See you.